it. I hope. Okay. Okay, it's a great pleasure to be here and to try to learn supersymmetry together with you. I mean, as Domenico said, please ask, like, just interrupt and ask. And also, you know, like, I am here, so in my office is there, it says lecturers. So you just, you know, if you are shy or whatever, or if you have a longer question that would take too long to interrupt, just come. And there is, of course, also this Q&A. I don't know what will happen in the Q&A. Last time I was here, we didn't have it. But anyway, there is also that. So I think, yes, this is the most important thing to ask. And today, the first lecture will be sort of like my hope is that you already know everything, but if not, it's okay. It will be a way in, so there will be no supersymmetry today. But maybe, okay, I want a little poll. Who is a master student here? Okay, so you are all mostly PhD students. And like, who has taken at least 2 courses of quantum field theory? Okay, amazing. So the first lecture is gonna be super boring, basically. But that's good, because that means that you know everything. Maybe I also get rid of this so that I don't make any accidents. Yeah, and also if I go fast or if I go to, like, whatever I do that is a bit crazy, just stop me, Elli, say, come on, stop doing that. Yes? Good. So maybe a little bit of a plan. Okay, today we will just start with preliminary stuff. I will just remind some things that I need you to know from QFT or a little bit basics of group theory. Then SUSY is supersymmetry, yes. So then we will derive the supersymmetry algebra, both as a minimal extension of the Poincaré, which I will introduce in a second, or and the extended supersymmetry algebra. The moment we have the algebra, is everything okay? Yes, I keep going. I will introduce its representations. Yes, massless and massive. The moment we have representations, we know which type of particles can live and how they are organized. And then the next step is to build theories out of this. So basically learn how to write down Lagrangians. And for that, maybe some of you have already seen some basic supersymmetry in components, but like we have 1 week, I will just go crazy all the way. I will immediately introduce superspace because this is also where all the nice things happen. And then having superspace, I will teach you how to build Lagrangians. I will begin with theories with minimal n equal to 1 supersymmetry, but I want to go all the way to n equal to 4 super Young-Mills, which you really need if you want to be able to do your ADCFT class. Yes? And then there is an item number 6, which actually most probably this will be in the 3rd week. There are 2 lectures there. And there I want to talk about quantum aspects. By the way, now also is a good time to say, oh, I cannot read your letters, you know, make bigger, whatever. Just say yes. And also, I guess this item we can negotiate also. So you have enough time to, it's not prepared. So you have enough time to influence what will go here, yes? I just say this. So just talk to me and say, I want this. So is everything all right up to now? Good. So let's start. I want to first, I'm sure you all know, but I want to slowly also introduce notation, maybe something important. So what to read? So, we are in Italy, and also I really like it because it's updated every year. So I will be the closest to the review or introduction by Matteo Bertolini. I guess most of you. Yes, maybe if you have studied something, you have studied from there. And I will more or less follow his notation, apart from one or two things that I strongly disagree with. But anyway, I will. It's okay. it's super minor. It's nothing. So yes, I will try to follow his notation. But just because also things are happening in the school in a very fast way. You have to learn everything in 3 weeks. There is a very nice, very fast introduction by Bilal. Adel Bilal. I just write fast and short. So if you don't have enough time to look at this, this is something sometimes I give to master students and they can go through it in a week. So this is really like quick. And there is another review that, I don't know, I used it also as a student by Liken. All of these things you just Google and you find, and you don't need to buy any book or anything, yes? So you just get it from the archive. The notation there is a little bit, maybe let's say old school, but actually super nice. So if you have the patience to go through the notation and don't get upset, this is very good stuff. Yes? Okay. So having said that, we begin. And again, I will mostly follow, this is not the notation I use when I write papers, but I want to use Bertolini. So I will use the Minkowski space, let's say maybe the Fino notation. Yes, I am sorry. But we should be able to copy something that we are all consistent with, so we will just do that. I have to say, I would really like, but I never had the patience up to now to make a big Mathematica file that you can put in everything and change your notations. But I never had the strength up to now to sit down and do it. So anyway, this is going to be my metric. And first we want to talk about Lorentz transformations. Yes. So like this, nicely. And they are defined as the transformations that leave the metric invariant. Yes? And what we do is that we can expand around the identity. So we will parameterize by parameters omega that are small. Okay, and here there is already a little bit of notation, yes? There is a choice made there. Maybe I already said the secret, but maybe who can tell me how many are the generators of the Lorentz group in 4 dimensions? 6. How do we calculate this? Let's do it in d dimensions. How do we do that? So these are d by d matrices that first we take all of the symmetric and then we subtract, right? Very good. So these are antisymmetric d by d matrices, yes? If it's too fast, you complain now. Okay, or you come and find me if you are shy. Yes? So this is the number of generators. And in D is equal to 4, we have 3 rotations and 3 boosts. Yes? And maybe I write already because I'm... okay, one thing. Sorry, I want to have a nice blackboard, so I should write here. So Greek goes from 0 to 3, yes? And then I will have an index I that goes from 1 to 3 and is only space. And the rotations are I. They will come like this. And the boosts. Oh. Yes? Can I erase this? Yes. And let's just write the algebra. So here there is also a little bit of the fact that I chose this metric. It comes to you, yes? Well, so I am mixing these guys. And then you antisymmetrize first with mu and nu because they are antisymmetric, and then with the fact that you have the commutator. Is it clear? If it's not and you are shy, ask or come later or Q&A. Yes? Fantastic. Very good. So now this is the Lorentz algebra. And to go to Poincaré, we just add translations. Yes, the generator of the translation is like this. And then for the algebra, okay, this is in the case that it acts on functions, yes? So this is one. And now I have to tell you how translations mix with Lorentz. Basically, they just get rotated as vectors, as 4 vectors. Is everything super known and clear? Amazing. So if we are happy with this, then we move on to representations. So I do this so that I say also all the words now for like a group that you know, so that when we do representations of SUSY, all the words are there. So when we want to study representation theory of any group, the first thing we need is to have a way to systematically label our representations. Yes? And when you learn group theory, you learn that you do this by the Casimirs, the eigenvalues of the Casimirs. So the Casimirs of Poincaré there are two. Maybe Casimirs mean that they commute with everything, yes? By the way, okay, I am already making spelling mistakes. I have a very bad dyslexia, so you are not gonna learn English from me, yes? You should just forgive me, yes? So there are two Casimirs. The first one is the square of the momentum of the translation operator, which is the mass squared, when we will do the eigenvalue. And the second one, okay, and here a tiny little bit of explanation is in order. Who knows what is W? Okay, amazing. Okay, more than half. Fantastic. So W is the Pauli-Lubansky vector. And this is the cool way Pauli found how to prove integrability of the hydrogen atom. Yes. So the symmetry is a little bit more for hydrogen than what we thought. So here is the Pauli-Lubansky vector. The epsilon Levi-Civita. Yes? Everything is clear? And then this vector, this is, if you wish, a tiny little homework to do. First of all, it commutes with translations. Yes? And this is another property to base. So now, the eigenvalues of these two guys, we will use them to characterize representations, yes? Yes? And this is good, and formally this is what you always do in this life. But in the case of Poincaré, this is a little bit of an overkill. We will do something actually much simpler. We will talk about the little group. Who knows what is the little group? Very good, fantastic. So, and maybe just a word, why do we do that? So Poincaré and Lorentz are non-compact groups. So there is a math theorem that says they don't have finite representations. So, yes, in principle, first sight, this is very bad, but no problem. Wigner told us what to do. He said, well, no problem. You go first to the res frame, you do everything there, and then you can boost yourself wherever you want to be. Yes? Yes. Is this all good? And the reason, and we will do this in 1 second, the reason we do this is from these annoying non-compact guys, The moment we will go to the rest frame, we will encounter just the little group, which has, it's a nice compact guy that has finite representations. Yes? Yes, so these are all the correct words to say. Are these words okay with you? Good. So let's do the little group now. So, and we will split. I will try to make a nice table. We will see if it's nice. We will split into massive and into massless representations. Massive we have this, and massless, obviously. This is just 0, but of course it changes something. That's why we are doing it slowly. And now we go to the rest frame. So what happens here? I can make a choice like this. Yes? So where this is a 3 vector. And here what I can do, I can make this choice. Yes? And what is the little group? The little group is by definition the symmetry that doesn't change these forms. Yes? So I write it in words first. These two forms. What is the symmetry here? What is the symmetry here? Fantastic. So now what is going to happen, because of this nice thing, we will label our representations with the mass or the energy for the massless case, and then the spin, or in this case, the helicity of SO3 or SO2. So here in this, so the table is continuing, yes? So here we have M and S, and here we have now here you can evaluate the two Casimirs, and this is the one, and this is the other. And here you can evaluate and you just get 0. So that's why we had to go a little bit slower, but it's okay. P mu. So the eigenvalues of the helicity are the eigenvalues of this operator. Yes? And maybe I should just say I take spin and I project it in the direction of the momentum. Is everything super clear? Perfect. So now we want to do, so you know, when you read Weinberg, for example, how he starts his first volume, he goes through all the different fields that you can write, and he tells you in which representation of the Lorentz group they live, and you can take this as a definition. The way they transform under the Lorentz is a definition of these fields. Yes? So we have okay, and here I will use also a little bit this to ask questions and make sure we know everything that I need. So first of all, what is a scalar? A scalar is a guy that doesn't transform. And by the way, even though it should be clear, I am annoying and I put 0 so that you don't confuse that when we do a translation, of course, you will get a correction to that, yes? So I just go to the origin, I do a Lorentz, and nothing happens. Now, quick questions. What is the mass dimension of, so basically I claim that up to factors, there is nothing else you need to know for learning supersymmetry other than mass dimensions and degrees of freedom. And okay, these little guys that we did up to now. So what is the mass dimension of a scalar? Yes, can you tell me in D dimensions? Fantastic. I'm just doing a little review, yes? Which is 1 in 4D. What is, how many degrees of freedom a real and a complex, let's do a real scalar first. 1, and a complex scalar, 2 real. Okay, nice, scalars, very easy. One tiny thing I want to add here. So when we do degrees of freedom counting, we will always count on cell and off cell. How many degrees of freedom we have on cell and how many off cell for the scalar? Just say a number. So it's the same. That's why you're not answering. And why is that? Because for the scalar, the equation of motion is the Clyde-Gordon equation, and the Clyde-Gordon equation does not impose any constraint on the degrees of freedom. Why? Because actually, it's a, so. Let's Fourier transform this equation. This is 0. Yes? So it doesn't, okay, sorry, there should be a minus. This is the difference between Minkowski and, anyway. No, Yes? No further restriction on the degrees of freedom. Nice. And now that we are very happy, we will go to spinors. Is everything okay up to now? Good. Okay, so what did we learn in quantum field theory 101? First, we learned the Dirac spinor, yes? And in some sense, if I follow Weinberg's logic, what is the definition of a Dirac spinor? I should give you the way it transforms. So psi, and I will try. So Dirac spinors will be represented by a capital psi, and the vial that will come in a second, they will be represented by small Greek letters, yes? So this is capital. So the way it transforms, and again, I am annoying and I put this 0 here. Capital. Yes, and of course, this is empty until I tell you what this is, which I will do in a second, yes? Now, I interrogate the same way I did before. First, what is the mass dimension? Sorry, loud. 3½ Can you tell me in D dimension? Thank you. What else am I asking? I am asking about degrees of freedom. So now we have to be a little bit nicer and separate between off cell and on cell. So let's start. Who will tell me this answer? For what? For real or complex? Complex. Because the psi in 4 dimensions is defined as a column with 4 entrants, if you remember, right? And on cell, and why this is happening? Because I impose the Dirac equation of motion. This is a matrix. This is a 4×4 matrix. This is for complex vector. So these are 4 equations that kill half of the degrees of freedom inside psi, yes? Is everyone happy with this? Fantastic. That's very good. We continue here. Okay, now I want to write the Clifford algebra. And to move on, because I want to now find the vial guys. Okay. I will follow the order of my notes anyway, because otherwise I will go crazy. I will choose a representation. So this is And we will see in a second, we will derive why this is like this. And in this representation, I will split my Dirac spinor into, so now these are the small letters. And like, please, I insist, alpha is down. Up. So this is in some sense a very innocent definition, but this is all the mistakes when you calculate supersymmetry stuff, is by putting one up down and then it's a disaster. You will never find a minus. Yes? So this is where we start from. And in order for this thing to make sense, I need to tell you what these babies are and where their alpha and alpha dot is. So again, this is definition, but this is very important. So we define this guy without any bar on it, with first an alpha and then an alpha dot. I will test in a second for you that this makes sense. And what is this? This is basically Pauli matrices, so the identity, and then the three Pauli matrices. Okay, I don't write the Pauli matrices, is it okay? You know them. Sorry, I'm maybe lazy sometimes. And then we want to define the bar guy, which is sitting here. And very importantly, this guy is defined with the indices up. And first come the dotted index, and then come the undotted. And this guy, what I will write here now, in some sense, maybe you know it and you will not even complain, but to make it perfectly super math perfect, it will be a little bit further down in the lecture, but I will just write it anyway now. I will raise and lower indices with the two epsilons, which, like in a little bit, I will tell you that they are okay to raise and lower with them. They will be a metric in a specific space that we will talk about. Yes? And if you do this calculation, you get a minus there and nothing else. Yes? And again, sigma has indices only down, and an advice from a person that has suffered a lot, never try to raise and lower indices of sigma and sigma bar. Just keep it where they are. Otherwise, it leads to hell. Yes? Yes, this is correct, yes. I'm sorry. Actually, here I want them to be beta. Yes? Sorry, yes, of course. Yes. And yes, it's perfect. Thank you, this is amazing. Yes, sometimes when I go happy, I will write things very fast. Maybe you fix. Yes, yes, you tell me. Thank you, that's amazing. Okay, so let's first, because I am defining things, but what's up with all of this stuff? Let's test that what I wrote there makes sense. So what I want to do is that I want to make this multiplication and see if things work out. So this is alpha alpha dot, and this is alpha dot alpha. So my alphas are becoming like feces, but anyway. And the definition we made was psi is always down, and chi bar is always up. Yes? So let's make this multiplication, and let's check if we define things properly. So this will hit here. Yes? And then this will hit here. Is it clear, or I am already making a mess? Is it clear? So, and here there is a little bit of a lesson in this life. When we contract undotted indices, again, this is a convention, but it is what it is, and we should never do anything else. We contract in this way. And when we contract indices that are dotted, we contract in this way. There is this east-west, but I have dyslexia, I cannot tell what is that. But it's visual, it's clear, it's this. Yes? Yes? So these are good definitions. Okay, so now we have our beautiful notation, and we are ready to start from the Dirac and make while. Let's discover first why we will do that. And what I am doing now, I'm doing it in 4 dimensions, but in any number of even dimensions, you can do the same trick. In odd, not so much. There is another thing to do there. So when there are even dimensions, you can define, okay, gamma 5 is called in 4, but it's equivalent, which is the multiplication of all the gammas. And if you do this, you get a nice splitting. These are 2 by 2 identity matrices. Yes? So this is a very nice guy with many nice properties. Amazing property number 1. It squares to 1. Another very good property is this. Because it's identity, when you dagger it, you get itself. And okay, I deleted already, but it doesn't matter. I wrote how Dirac matrices transform under Lorentz, and I also said that unless I tell you what is sigma mu nu, this is empty. So, who can tell me what is sigma mu nu? Honestly, I heard one person can tell one person who is brave enough to take it on them. Amazing. Yes. So this is, I don't know, Peskin and Schroeder, yes? Amazing. And then we have our beautiful notation. I will first write, and then I will explain. So this is in Weyl representation. Okay, something that should have gone there, because it doesn't need this, is just with this. And this is super crazy important, is this, that gamma 5. This is what we need in order to define while. Yes? So keep it in mind 1 second. Let me just write what these babies are. So, by the way, this, you just multiply. Yes, you just, so what I will write here is no magic. By the way, this is one, I mean, completely stupid difference, but difference with Matteo Bertolini. He doesn't put his eye there, he puts it in the definition. But whatever, I put it here. So here, we have a contraction of the dotted index, and it follows the rule, yes? If I ever don't follow the rule, you scream, yes? And from the second part of the commutator, again, the same alpha, alpha dot. I think I wrote everything, I didn't forget anything. All of my indices are in order. So maybe let's stress here this object. It has indices alpha, but I will write it. It's good to give some space between them so that when you will do your contractions, you can see what contracts with what. And you see already that the second index is up, so that I can multiply with something next to it and have the right way of contracting, yes? And now the bar. Yeah, usually it's nice to just write out and then put the indices, because this is faster. So this guy has to start alpha dot alpha. And then you repeat yourself. Alpha, beta dot, alpha, beta dot. Yes? And also let's write nicely, what are the indices of this guy? Yes, first comes. Yes, tell me, what did I do? Yes. Thank you, fantastic. Is everything perfect? Everything makes sense? And again, this matrix is made such that it has the beta dot down, the second index down. So when I will do my matrix multiplication, it will multiply whatever will come with an index up in the according, right? And if we follow these rules, we never make mistakes. And I write it here. Note, it will come back to us that sigma bar nu nu, or like this, is equal dagger. You can do it as a homework if you don't believe me. Nice. I will delete this. Just a quick question. How many of you have already seen these things? Okay, fantastic, amazing, 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 amazing. So what have we learned by all of these things that I said? First of all, very beautifully, especially because of this relation, we see, and you can test it by yourself, that the sigma mu nu already we said is a representation of the Lorentz generators, so it obeys the Lorentz algebra. But because this guy is diagonal, also the sigma and the sigma bar obey the Lorentz algebra, yes? So they are different representations of the Lorentz algebra. Now, we also have the beautiful gamma 5, which squares to 1. And because it squares to 1, we can use it to define projectors. Like this. Yes, and this is very nice, because if I have, which one? Yes. Whatever. So this is very good. So these are my two Weil representations, the left and the right or whatever. So what is happening? The Dirac representation, the correct words is that the Dirac representation is reducible to two Weil representations, which are irreducible. I will write these words. Words are also important. So it's reducible. And you can maybe write schematically D is equal to the left and the right Weil representation. Yes? So now questions, quiz time. Sorry, what happened? I didn't ask yet. Is there a question? Okay, quiz. How many degrees of freedom a Weil spinor has when it's off cell? Thank you. A non-cell? Fantastic. Very good. I go there. If you know all of these things, this means that you took a very good quantum field theory class, and you should be grateful to your teacher. Buy them chocolate when you go back. So just one last annoying thing, that I will write it and then you should not allow me to delete because we will use it afterwards. So under Lorentz, okay. Yes? Yes, so please don't let me delete this blackboard more or less until the end. Yes, very good. So here we also see very explicitly that these are two independent representations. Yes, they transform independently. Okay, we are more or less, yeah, we are more or less done with spinors for now. Quick quiz, we continue with the quiz. Okay, the next guy in the next item in the fields list is a vector. Yes, which it's called vector because it transforms as a vector under Lorentz. Amazing. So, okay, I'll just try it. But what I want from you is, and you can start thinking while I'm deleting, I want, what I did before. I want degrees of freedom and mass dimension. Think until I delete the blackboard. And I want it on cell, and I want it also off cell. Yes, so we have a vector. So, degrees of freedom. Yes. Yeah, massless for now. Very good. Can I have numbers? 4, yes. Okay, I say loud what he said. So very naively, you say 4 because it's 4 things, 4 real things. But because there is a gauge redundancy, some parameter, let's say alpha. I don't know if alpha now is a good name, but whatever. -1, we get 3. So this is because of this. And what about on cell? Yes. And you know this very well because when you study the electromagnetic waves, you see you have only the transverse in the end contributing and the longitudinal ones goes away. Yes? And if you want to show it more carefully, you should write, polarization vectors, blah, blah, blah. Yes? Good. We skip all of these things. There is something very important. I will write it here. Here you can test one step more your quantum field theory class, if you should be extremely grateful to your teacher or not. So there are these properties of the sigma guys. Have you ever seen this? Who has seen this? Okay, not bad. So this is a self-dual, and this is anti-self-dual. And this is very important when you will go to learn instantons or when you have already learned instantons, because it allows you to split to plus or minus, there is a half, yes. And why do I say this? I want that we know this. So when we have in this language of Lorentz with the 4 vectors, and so this is an antisymmetric tensor. How many degrees of freedom an antisymmetric tensor has? Sorry, loud? 6, very good. I can now actually project it using these beautiful guys to a self-dual and to an anti-self-dual part. So now this is by definition my, let's say, self-dual part. So which immediately obeys this equation with a plus. And then indices are down. This is the anti-self-dual part. And so F mu nu is 6 degrees of freedom, which in this way I split to 3 plus 3 degrees of freedom. Yes? Is this okay? Also from the people that didn't know this before? By the way, I had a minus sign here that I left it on purpose when I saw it, but okay. You can check your notes. There was a minus sign wrong somewhere. Here. Anyway, it's okay. Instead of writing minus plus, I wrote plus minus. So, question for you. I didn't forget. What is the mass dimension of F mu nu? Loud. D? D plus? No. But okay, this is, okay, so F mu nu, one of the ways you, maybe I write like this first. What is F mu nu? This has to be consistent with math. Is a commutator of 2 covariant derivatives, right? So what is the mass dimension of this gadget? 2. Because of this. So what happened? There is a problem here. So you wanted to be correct, but something happened. So the reason why you said this to me is because the kinetic term in the Lagrangian is this. So you said d dimension, we split, yes? But the way it actually works is, because this is secret, the mass dimension goes to the G. Young-Mills, yes? And this is how you know when something is marginal in 4 dimensions or relevant, irrelevant as you go up and down. So is everyone happy? Okay, I will write super quickly what is Majorana. We will never do this in this. I will never. Who knows what is Majorana? Okay, I skip it. Who wants me to do Majorana? No one. Good. If you are shy and you say no, you can ask me later, yes? I will tell you. Okay, let's do the things that we really need. Okay, so now, if you know, like, if most of you know all of these things, most probably the thing that I will say now you will also know, but we really need to say this to make everything nice. So, the Lorentz group, and okay, now I will say. First, we talk about the algebra. So what I am supposed to be doing here is that I am writing small letters as opposed to capitals. So this means that this equation is at the level of the algebra. Yes, so this is an algebra relation. Who knows this? Everyone, no? Yes, fantastic. So it's very simple. I just write it just for the fun of it. We just define rotation plus boost very nice, like this. So the only difference is the minus sign. And we can check a few things. One thing is that the JIs, left or right, okay, yes. So this is one. This is the SU2 left. This defines an SU2 right. Yes? And very importantly, J left with J right with whatever index you want is 0, so they are really two separated, yes, completely decoupled SU2 algebras. So this is very important. And one more important thing is that J left for any index daggered is J right, and the other way around. Yes? And this should really remind you of sigma mu nu and sigma mu nu bar. Yes? So we are, yeah, we are building on everything nicely. Is everyone happy with this? Now, next step. So here I wrote very carefully that these are small letters, which means that is there a question? No. Which means that we are, oh, at the level of the algebra. So now I will write another equation, which I will write capital letters, which will be at the level of the group. And if you know this, you should really be grateful to your QFT teacher. So this usually is not in the QFT class. Then you really go and thank. Yes? So these are capital letters now. So who knows this? Oh, yeah, you have to go thank. So what does this mean? This means that there is a homomorphism between Lorentz and this guy, yes? And this is very much the same what we learn in quantum mechanics between SO3 and SU2, yes? And what is important is that this is a 2-to-1 map, and we will do it in like now. But I write some words. 2-to-1. 1-to-1. I just write this to contrast it. Yes? Okay, you all know this, but I write it anyway. So this is the group of 2 by 2 matrices with complex entries. And for me, it's important, and that's why I write it. My matrices, I put my spinor indices like this. Yes? Complex numbers with, so the parentheses, and to establish the homomorphism, we need to have that if I select 2 matrices inside the SL2C, yes, then there are maps and not just they are such that when I multiply, this can also be done like this. And then everything is good. Yes? Now, the only thing that I need to do to finish this job is that I need to show the 2-to-1. And I will do this very quickly by deriving the relation between lambda and m. But before we do this, let's build a little bit. So first, and this is again the same when you learn SU2, SO3, you can take the 3 x1, x2, x3, and you put them in a matrix. So I do the same here. I will define a matrix X, which if you write the components, it will have alpha and alpha dot. So this is definition. So we are using our friends, yes, to go from a 4 vector to a 2 by 2 matrix. And the first thing we need to notice first of all, we need to check that everything is all right. So the first thing we do is we take this 2 by 2 matrix, we form its determinant. Oh, I didn't write it. Let's be careful, yes. So here I need to check my notes because the specific sign have to do with the choice of the Pauli matrices. Okay, there is a parenthesis here. Which is the invariant under SO 1,3. But we can also prove this in the SL2C language. How do we do this? So again, this is my matrix. I have to assign how it transforms. And of course, I have the indices, so it's clear how it's going to transform. It's going to transform like this. Maybe I just say m bar is equal to m dagger, and this is still an element. We are just consistently with our previous notation. Whenever we dagger something, we use dotted notations. And now, if we know this, we take the derivative, the determinant. So determinant of x goes to determinant of m, determinant of x. Yes? But these are one by definition. So the determinant is invariant. Yes? So we have everything amazing and consistent. This is from SO 1,3. This is from SL2C language. Is this clear to everyone? So, what is going on? I already wrote it here. We have a map, which is this sigma guy. So you can say if you were a mathematician, you would write, you have a map from 2 by 2 matrices to 4 vectors, yes? And now, for what I need to do, I will need the inverse map. Yes? I need to learn how to go from 4 vectors to 2 by 2 matrices. How am I going to do that? Clearly, with my sigma bar. That's the only thing that I have left in this life, yes? But it's a little bit more than just that. Basically, I will use this equation. How do you get this equation? Can someone tell me? If you don't tell me, I will tell you, but can someone tell me? You can just go to the Clifford algebra, gamma mu, gamma nu, eta, and plug in and take the trace. Plug in the 0, sigma, sigma bar 0, and take the trace, and you will get precisely this beautiful guy. Yes? So actually, what is the inverse operation of sigma mu? Is trace of blah, 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 whatever, sigma bar nu. This is the inverse. So if we have a 4 vector and we want to get a 2 by 2, we do this to it. Let's do it. Let's check that this is indeed true and I'm not lying. Yes. Yes, it's the opposite. I just realized this. Yes, yes. Let's fix it. Yes, yes. So these maps were supposed to be like this. Sorry. Yes? So let's do this. And in fact, because of this 2, the really, really inverse is like this. Yes? So let's do this. Amazing. So I want to know what is this. How do I know? I plug in what I have, the only thing that I know, which is this equation. So now this is small, now this is the coordinate. Yes, this is a little number, it goes out. Yes, so this is gone. And now I use this equation and I get eta. Okay, I'm not so amazing with what I am. Let's put this down. Yes. Correct. Yes? So now we have everything we need in order to derive this equation. But let me first write it. So this is what I want to have. And why do I want to have it? Who has seen this equation before? Okay, it's good that I'm doing it. Why this is good? Because here you see the 2 to 1. So if you have m or minus m, it gives the same L. Yes? So this is the 2 to 1. Look! 2 to 1 map. Just look. Okay, let's prove it very quickly. Yes? I mean, we could leave it as an exercise. Let's leave it as an exercise. And if it's time in the end, I do it. You tell me, Elli, do it if I finish. Okay? Yes? It's very easy. Maybe I skip this. Okay, I think this is amazing. So now we have covered everything in some sense that if you have taken the best possible quantum field theory class you have learned. And we just now need to say a few things, some names. And here we will go back to this blackboard. I will change the title. I want a better one. So we have everything. First of all, this I can now identify. It's gone, but it doesn't matter. As my matrix M, so remember, this is the upper component of the Dirac matrix that we picked up. And this transforms with this 2 by 2 matrix that you can check is a SL2C matrix. So here I write it. So you can think of this as the fundamental representation of SL2C. And here, by recalling that sigma bar mu nu is equal to sigma mu nu dagger, you can identify this as a complex conjugate representation. Or just conjugate, whatever. The conjugate to the fundamental. Now, there is another thing to remember, which we also did. We had also this relation between SO1,3 and the two SU2s, yes? And if you remember, we had that the SU2 left, they are also complex conjugate to each other, yes? So what we will say is that this spinor here that we identified with the fundamental representation, we will label it as half zero, where what this really means is that this is the spin, I write the spin of the SU2 left, and this is the spin of the SU2 right. Yes? So this spinor is in a doublet representation of SU2 left, and it's in a singlet representation of SU2 right. Yes? Should I write this in words? I write it here. And I will write upstairs again, but let's write now the words here. Okay. These are the words. If there is anything strange, just say it's a matter of notation. Here, maybe I recall that M bar. If you are not happy, ask me. Is everyone happy? Okay, now I will also tell the very important why epsilon alpha beta is a metric. So we use the definition of the determinant with tensor indices, right? And maybe to not write too many equations, I just write straight So this comes from the definition of what is the determinant in terms of tensors. You just multiply the epsilon from the other side. Yes? But again, because we are in SL2C, this is equal to 1. And this equation is the same as right? The same thing, like the metric is invariant under the SO 1,3. So epsilon and the same for the dotted guy. Yes? So having this, we will do a tiny little bit more. So now we can define what is psi with the index up. Yes? Like this. And when we have this guy, the same way we say x squared, and we say that this is invariant, the same way now we can have psi alpha, and this is invariant. Maybe I write. Yes? Totally stupid, obvious? And what does this mean also? Totally stupid, obvious? It means that psi alpha up transforms with the inverse, m to the minus 1 beta, alpha under SL2C. Is this obvious? I don't want to kill you now in the end. And in identically the same way, we have epsilon alpha dot beta dot, with which we can define this is what we started with. There is a dot here. In the Dirac spinor, we lower the index. And how this transforms? Yes? Am I making the indices okay? Yes, I think so. Okay, now everyone seems very quiet and writing down. Is this okay? And note how I am a very good girl and I am contracting my indices the way I told you. I am never doing anything else. So I stand by my word. Yes? Almost. 1 o'clock I finish, yes? I mean, we have everything now, we are amazing. Yes. No, it's okay. I am Greek. Is this wet? Okay, so something else that, like, okay, I write and then either you complain or it's obvious and natural. So, is this 100,000% clear or I explain it? So look what I did. When I just complex conjugate, remember in the Dirac notation, this was the upper part, so this is the 2-column, yes? So it's a gadget like this, and it's multiplied by this 4x4 matrices M from this direction, yes? Now, this guy is the guy we defined. So in the Dirac notation, psi bar alpha dot up was a gadget like this. Yes? So this gadget with the index down is down and it's multiplied from this way. Yes? So that's why we write these two equations this way. So this object is an object like this, and it has to be equal, I delete this matrix, with an object like this, because this is the object we had in the Dirac matrix. Yes? Now, here, when I dagger, I star and I transpose. So if this is my natural guy, which is like this, if I transpose it, I get an object like this, and that's why this went down. Is everyone happy with this? I don't know. This is the most visual way I explain it to myself. If you were a mathematician, you would take it as a definition, but we are not. Yes? Yes. And in the last few minutes, I want to just say higher representations of SL2C. Maybe here. And it's nice that we have the Q&A because we can also talk more about all of these things if there is something strange. Yeah, when we learn group theory, we need to make everything together from our fundamental representation. And in this case, we have the fundamental, our 1/2, 0 psi alpha, and we have the conjugate representation, which is the 0, 1/2, which is this baby. Yes? So can we use them to make higher representations? Let's first make a vector. We already have seen how to make vectors. But let's make it in a group theory way. How am I supposed to do this? It has an index alpha and an index alpha dot. So let's just take this and multiply it by this. Yes? So what do I get when I do this? I get this. And if you can say in this notation, this is a definition of a vector. Yes? And maybe I write a little equation here. Like my indices are bad. So this is the 2 by 2 matrix. And this is the A mu, the 4 vector. Okay. And one more. Is this okay? Is this clear? And what is also important is that you can check that this equation, both in the left-hand side and in the right-hand side, transforms as promised. And what is as promised? 4 vectors in this notation transform with m from the one side and m dagger from the other side. Yes? This is very important. That's why I wrote this equation down. Transforms as promised. Okay, and then one more such example. What happens when I do this? And of course, you can do the same with a conjugate representation for yourself the other way. So who wants to tell me what to write? 0? Perfect. Is this clear to everyone? So these things, they are independent SU2s. So I use the SU2 multiplication the way we learn in our whatever, quantum mechanics, yes? So now let's understand what is this stuff. This is important. So first of all, this is a singlet under everything. But this guy is a triplet under the one of the two SU2s, the left here. So this is a self-dual tensor. This is why I wrote this F mu nu stuff. I write and I... where are my indices? Sorry. No, I will. I think it's okay. How do we do this? I multiply two SU2s left. This is a singlet. Here there is contraction within, yes? When I write this. Okay. This is good. And then I have my indices are correct. Yes. And this is the object that I told you transform in a self-dual way. Yes? Amazing. Questions? And you can continue, and now you can go crazy. You can tensor as much as you want, and you can make whatever representation you ever wanted in your life. If there are no more questions, that's it. And okay, we have Q&A, so it's okay.
Okay, thank you very much.